Hello, bright minds. Have you ever wondered how those fancy gadgets like microscopes and telescopes actually make tiny or faraway things look so much bigger? Well, welcome to the magical world of optical instruments. Here's a little fun fact: light waves are like tiny messengers that carry images to our eyes, and optical instruments are the clever tools that help us catch and read these messages with more detail. Optical instruments are devices designed to process light waves, whether through reflection, refraction, or diffraction, to enhance or analyze images. Broadly speaking, they come in two flavors. First, simple instruments like the human eye itself or a magnifying glass, which rely mainly on a single lens or mirror. Then, we have complex optical instruments such as microscopes and telescopes, which combine multiple lenses or mirrors to achieve higher magnification and resolution. One important concept here is angular magnification, which compares the angle subtended by the image to the angle subtended by the object at the eye. Mathematically, it's theta prime divided by theta. This tells us how much bigger the image appears compared to the actual object. Another key parameter is resolving power, or how well an instrument can distinguish two points as separate. All these instruments use the fundamental lens and mirror equations and principles of image formation with curved surfaces. Think of how a spherical lens bends light to form images. Understanding these basics will help us explore how your fancy optical tools work and why they are so important in science and daily life, from reading tiny texts with a magnifying glass to gazing at distant stars through telescopes. Welcome back. Let me start by saying that your eye is nature's own optical instrument, yes, the original and the best one. Your eye works very much like a camera. It has a cornea and a flexible lens system that together form a real, inverted image right on the retina, which is like the camera's sensor. The eye lens is special because its focal length isn't fixed. Thanks to tiny muscles called ciliary muscles, it can adjust its shape to focus on objects at different distances. This process is called accommodation, a fancy word meaning your eye can zoom in or out by changing the lens thickness. Now, your eye has two special points that define its range of clear vision. The near point is about 25 centimeters, which is the closest comfortable distance you can focus on. Then there's the far point, which for a healthy eye is essentially infinity, meaning you can see distant objects clearly without straining. In the diagrams you might have seen, different eye defects and their corrections are shown, which help understand how lenses fix vision problems. Pretty useful to know, especially if you or someone you know wears glasses. So, your eye is not just a passive receiver of light but an incredible and dynamic optical instrument, adapting constantly to what you want to see. Let's talk about some common vision defects. After all, even the best optical instrument has its hiccups. First up is myopia, or nearsightedness, where distant objects appear blurry because the eye lens focuses them before the retina. Imagine trying to look at a distant object but your eye's zoom is stuck on nearby. Annoying, right? We correct this using a concave lens, which diverges the incoming light rays just enough to push the focal point back onto the retina. The power of this concave lens is given by -100 divided by the focal length in centimeters. Remember, this power is negative because concave lenses spread out the light. On the flip side, we have hypermetropia, or farsightedness, where near objects are hard to see because the eye focuses light behind the retina. We fix this with a convex lens that converges light, and its focal length is the reciprocal of the lens power, meaning focal length equals 1 divided by the positive power. Then there's presbyopia, a sneaky aging effect where the eye loses its ability to accommodate, making both near and far vision tricky. Bifocal lenses, which have two different lens powers in one lens, are the usual fix here. Lastly, cataract causes the eye's natural lens to cloud up, blurring vision. The treatment? surgery that replaces the cloudy lens with a clear artificial one, restoring sight. These defects and their corrections are perfect examples of practical optics improving lives. Now, who hasn't had fun peering through a magnifying glass? This simple magnifier uses a convex lens to produce a virtual, erect, and enlarged image within the near-point distance, making tiny things easier to see. The angular magnification, or how much bigger the image looks, is found by the formula 1 plus d divided by f, where d is the near-point distance. Enter your trusty 25 centimeters, and f is the focal length of the lens in the same units. This formula applies when the image is at the near point, so your eye is comfortably focused. Alternatively, if the image is formed at infinity, giving your eye a relaxed stare, the magnification simplifies to d divided by f. Keep in mind, lenses with smaller focal lengths offer higher magnification, but there's a trade-off. The field of view becomes smaller, meaning you see less area at a time. Still, this simple lens is a powerful optical tool that lets us explore the details in stamps, insects, or even a map. Ready to dive deeper into the microscopic world? The compound microscope is your gateway there. It cleverly combines two lenses, the objective, with a short focal length and high resolving power to create a real, magnified image of the tiny object, and the eyepiece, which then acts as a magnifier to enlarge that image further. The total magnification is the product of the magnifications of these two lenses. Mathematically, it equals the tube length L divided by the objective focal length f sub O multiplied by 1 plus d divided by f sub E, where d is the near-point distance and f sub E is the eyepiece focal length. Increasing the tube length or decreasing the objective's focal length ramps up magnification and resolving power, where resolving power, inversely related to numerical aperture, determines how finely you can distinguish close details. This is why microscopes are indispensable in biology and materials science, unraveling the intricate details invisible to the naked eye. Picture looking at cells or the surface of a mineral. The microscope opens up a hidden universe just for you. Let's now explore the giant lenses in the sky, astronomical telescopes. When you gaze through one, the objective lens collects light from a distant star and forms a real image at its focal plane. The eyepiece then magnifies this image so your relaxed eye can view it comfortably at infinity. In the normal adjustment setup, where the final image is at infinity, the magnification equals the objective focal length divided by the eyepiece focal length, so a longer objective lens and a shorter eyepiece lens mean more zoom. Typically, telescopes use to convex lenses and rely on angular magnification to enlarge distant celestial objects. The images formed are inverted, but that's perfectly fine in astronomy since we are mostly interested in details rather than orientation. However, when erect images are required, like in terrestrial telescopes, additional lenses or prisms are introduced to flip the image right side up. It's like having your personal spaceship telescope to unravel the mysteries of the universe. Now, binoculars, those handy gadgets perfect for bird watching or sports, are optical instruments with a twist. They incorporate prisms, such as poroprisms, which cleverly fold the light path, making the design more compact while also erecting the image. These prisms use total internal reflection, bouncing light around internally without loss, reducing aberrations that lenses alone might cause. The erecting system is crucial for terrestrial viewing, where seeing the image the right way up matters. The magnification formula remains the familiar objective focal length divided by eyepiece focal length, but the presence of prisms makes the binoculars more user-friendly. It's like giving your eyes an optical workout while keeping everything neat and convenient, definitely a fun and practical application of optical principles. Let's wrap up today with some must-remember formulas and ideas. For the simple magnifier with the image at the near point, magnification equals 1 plus d divided by f. If the image is at infinity, it's simply d divided by f, easy to recall. For the compound microscope, magnification equals open bracket L divided by objective focal length close bracket times open bracket 1 plus d divided by eyepiece focal length close bracket. And for telescopes in normal adjustment, magnification is the objective focal length divided by the eyepiece focal length. What ties all these instruments together is their use of image formation through refraction or reflection to enhance the angular size of objects so that our eyes see more detail. The human eye acts as a reference point, comparing angles to quantify magnification. Remember, higher magnification alone doesn't guarantee better performance, resolution and proper illumination are key. Complex instruments also involve cleverly combining lenses, auxiliary optics like prisms, and systems to erect images, making them both powerful and practical. So, next time you zoom in on a tiny insect, gaze at distant stars, or put on your glasses, you're witnessing physics in action. That's it for today's exciting journey into optical instruments. Physics is not just equations but the magic behind how we see the world, fun, fascinating, and full of surprises. See you in our next session.